Hi there everyone. In this video, which is the second video on transformation matrices, we're going to take care of the other things that we didn't look at in the last video. So just a reminder of what the syllabus says here. We're looking at matrices and how we can use matrices to transform shapes. We went through in the last video a number of different matrices that we could use to do that, to do reflections and rotations, and how to work out what those matrices are, and the effect on a shape, and how to actually do that with matrices. To apply a matrix, so we pre-multiply by the matrix, times by the matrix that represents the coordinates of the endpoints of the shape, and that gives us the coordinates of the new shape that we get. So I'm going to look at 1.7 now. I didn't do it in the last video, which is what about if you have two combinations, a combined combinations, which is what 1.7 talks about here. And we talked about in the last video about the relationship between the determinant and areas of shapes. So just remember from the last video that the scale factor for area for two shapes here is the same as the determinant of the transformation matrix. So let's look at this problem here where we've got a triangle and we want to transform it using that matrix there. That gives us another triangle, and then we're going to take that transformed triangle and transform it by another matrix, and then look at how do we go from the first one to the last one. Okay, so we've got 0, 1, 1, 0 here for our transformation matrix. Now again, I don't know what that does. I'm looking at that, I have no idea what that does, but I can apply it and have a look at it. That's one way of doing it. So I can say 0, 1, 1, 0, times it by the matrix that represents the endpoints. Remember, I'm going X at the top and Y at the bottom. And that then gives me 1, 1, 3 on the top, 2, 5, 5. So I'm assuming here that you know how to multiply two matrices together as well. All right, so I could draw those out. I could draw that triangle. I could draw this triangle here. So this triangle is now 1, 2, 1, 5, and 3, 5 is that new triangle that we've got there. Another way of looking at this is you can see that the x values have become the y values and the y values have become the x values. So we've just swapped the x and y values around. If you remember, what that will do is actually a reflection in the line y equals x. And that's what this matrix here represents, a reflection in the line y equals x, just swapping the x and y values around, which is what we do when we want an inverse function as well. We just swap the x and y variables around, and that's a way for determining the equation of the inverse function. Okay, so that's what that one is, a reflection in the line y equals x. Remember, the other way I showed you how to do this kind of thing is to just consider the unit vectors. So start off with our identity matrix and just think, okay, what's gone on to take our identity matrix to this one here, okay? So what have we done to do that? If we look at a little graph here, so we've got 0 or 1, 0, that one there, and we've got 0, 1. Okay. Now what's happened to the vector 1, 0 has become 0, 1, and the 0, 1 vector has become 1, 0. So they've swapped around. And you can see that if you include 1, 1 as well and think about the unit square, then that will stay put. So these two swap over, this one, and this one stays put. So a little bit more difficult to see, but that is actually just a reflection in the line y equals x. Here's the picture of that. You can see A, B, and C there transformed onto A1, B1, C1. So you can draw it out like that as well. Now that works fine. And that is a reflection in the line y equals x. Okay, second part of the question says transform that new triangle using the matrix 0, -1, 1, 0 and label that triangle A2, B2, C2. Again, doing the same thing. So we take our transformation matrix, times it by these new set of points, and we get those points there. If we draw it out, that's what it will look like there. Okay, so we've taken this triangle here and we've now got this triangle over here. You can see to go from this one here to this one here is a rotation 90 degrees anti-clockwise about the point 0, 0. So that's what that second matrix there represented. Now, the question then asks us to consider how do we start with this one and go to this one? Again, this is pretty simple. We can see pretty clearly that that is just a reflection in the y-axis. Okay, and if we can work out what a reflection in the y-axis looks like, we can work out the matrix. Okay, and that's what it wants. The question says, what is the matrix that takes us from A, B, C to A2, B2, C2? Okay, so here's the way you do it using those unit vectors. Start with 1, 0 and 0, 1. 1, 0 with a reflection in the y-axis will become negative 1, 0. The point 0, 1 in the reflection in the y-axis will just stay as 0, 1. Hence, this is the matrix here that represents a reflection in the y-axis. Easy. Another way of doing that is to consider if you have this transformation followed by this transformation here, A then B. The way that you can do the combined transformation is the matrix B times A. So you can actually multiply the matrices together. So remember, the order there is the other way around. So if you do A first then B, this is the order that has to go in. If you do 3 in a row, let's say A, B and C, so a rotation, a reflection and an enlargement in that order, the matrix that you need to calculate that does that would be C, B, A. Now let's just see if that works for this particular example here. We started off doing the matrix 0, 1, 1, 0. That represented our reflection in the line y equals x. And then we did B, which was a rotation 90 degrees anti-clockwise centered at 0, 0, which is 0 minus 1. That should be a 1 there, shouldn't it? 0 minus 1, 1, 0. Okay. 0 minus 1, 1, 0. Okay, let's multiply those two together and see what we get. So we've got minus 1 up here, 0 here, 0 here, and 1 there. So you can see that matrix there represents the combined effect of, I won't label that one there, of doing this matrix here first, followed by this matrix here. And you can see that is the same as our answer that we got for just looking at it and working out that it was a reflection in the y-axis. Here's another example that covers a very similar idea. We've got a triangle transformed by this matrix. Then that triangle is transformed by this matrix. Again, these are not standard transformations. I'm looking at these, I'm not quite sure what exactly these things are doing, so these are harder to draw. We want the single matrix that transforms the original to the second matrix. Okay. So if we say that that's matrix A and that's matrix B, the order is critical here. So we've done matrix A first, then B. So we've got to work out B times A. Remember, it's the opposite order. You start from the right and work backwards. So B times A will be the matrix that we need to work this out. So 2, 0, 1, 2, and 1, 3, 0, 1. So in the last example, we could actually see what the transformations were. They made sense. They were reflections and rotations. Here, don't know what these ones are, so you have to understand and know how to do this technique. So 2 times 1 plus 0, so that's 2. We've got 6 plus 0, so that's 6. 1 in the corner, and 3 plus 2 is 5. So that matrix there, BA, represents the combined transformation. So if you were just to apply this matrix here to the original set of points, you'd go straight from the original triangle to the second triangle. Another cool idea with these transformations is when we talk about the inverse matrix. So if we have a matrix like, let's say, this, that performs a certain transformation, the inverse of that matrix performs the inverse transformation. So if this matrix does something to a shape, the inverse matrix will take it back to its original form. Okay, so this matrix here actually represents an enlargement, a dilation of scale factor 2 centered at 0, 0. So if we looked at the inverse matrix, okay, so 1 over the determinant, which is 4 in this case, swap those two around and change the sign of those two. So we actually get a half, 0, 0, a half. Okay? So, whereas this matrix is an enlargement scale factor 2, makes the shape bigger, this matrix here is an enlargement scale factor a half, so it dilates the shape by a factor of a half. So you can see that by multiplying those two together, you get back to the original shape that you had at the start.